Hola amigos, welcome to our last video for this unit. This video is called FreeFall. FreeFall is when you have an object and you let it go and you let it just fall to the ground. Okay. There's a force that actually pulls that object towards the ground, and that force is known as gravity, which I'm sure you've heard of before, but you probably have not heard of acceleration due to gravity. What does that mean, acceleration due to gravity? Well, gravity pulls an object towards Earth, but it doesn't pull objects at a constant speed. It actually pulls them, and their speed increases due to gravity's pull. Well, you know, when speed changes, then that means acceleration. So acceleration due to gravity is our speed changing for our object, and the number that represents acceleration due to gravity is negative 9.8 meters per second squared. Well, what does that mean? It means if you drop an object, its speed is going to speed up 9.8 meters per second every single second. Okay, so their velocity will increase 9.8 meters per second every second. So if you drop, here's a basketball. If you drop this basketball, and at the beginning it had 0 meters per second, meaning it wasn't moving at all, you just held it right here and then you dropped it. When you let it go, after the first second, the speed would be 9.8 meters per second. After the second, it's going to be twice that amount because we are going to increase our speed. Velocity will increase 9.8 meters per second every single second. So we just continue to add on 9.8 meters every single second. And that happens regardless of the object. So this basketball will have a speed of 9.8 meters per second after the first second. Same thing if I took a wad of paper. This is supposed to be a wad of paper right here, okay? Well, if I dropped it and it started at 0 speed, after the first second it would have the same speed, 9.8 meters per second. And then it would increase every single second just like the basketball. And we can actually test this by taking a wad of paper and a basketball and dropping them at the same time, and they'll hit the ground at the same time because they increase with the same acceleration. So this is a number that you will need to have memorized, the acceleration due to gravity value. So I was talking about taking something and just letting it free fall. So a free fall diagram is basically just what I drew above. You draw your object, you draw an arrow, okay, and a couple things that you will want to draw in your diagram is any information that I gave you in the problem. So if I gave you the initial speed, you're going to write that and label it VI right next to the object right before it was dropped. Okay. If I give you distance, the change in distance from start to finish, or the change in time, then you're going to put it right next to the arrow. If I gave you the final velocity, you're going to put that down here right at the bottom arrow. Now, there's something I need to clarify about final speed. So here's the ground. When I drop this object, let's pretend I'm dropping something very heavy that's not going to bounce, okay, like maybe a bowling ball. If I drop something very heavy, when it hits the ground, the second that it actually touches the ground, what's its speed? Well, it's 0, right, because it's not moving anymore because it hit the ground. So when I'm talking about final speed, I am not talking about the speed when the object actually touches the ground and is at 0. When I'm talking about the final speed in a free fall, I'm talking about the speed the second before it hits the ground, okay? So final speed is the second right before this object actually hits the ground. We actually call that terminal velocity. So I'm going to write that right up here. That's a term you need to know. Terminal velocity is the speed of an object right before it hits the ground. We can also refer to terminal velocity of an object that has its speed right before, like, it hits a wall. Basically, it's the speed right before an object actually stops. So in this case, your terminal velocity is not going to be 0 because we're not talking about, you know, it actually touching the ground. We're talking about the speed right before. Okay, another type of diagram that I might have you draw is a diagram where I'm throwing it downward. So here's my object, okay? It will accelerate due to gravity, but it starts at a speed. If I'm having you draw a diagram of an object that was thrown, I want you to draw an arrow right before the object, meaning that the object was thrown with a velocity. So if it's starting at rest, like this object right here, okay, the free fall object, the velocity will always be 0 because free fall means you started at rest and then you let go, okay? But if you're throwing it downward, your initial velocity may not be 0. It might be something else. We may not know what it is. Okay? And then again, your distance needs to be labeled right next to the falling arrow, and your time should be labeled here, and then your final velocity also should be labeled in the same area. Final velocity is your terminal velocity. It's the speed right before it hits the ground. Okay, now I can kind of combine these a little bit into another type of diagram. That's if an object is thrown upward. Okay, so here's an object. Okay, it's thrown upward. If it's thrown upward, that means we need to put an arrow here saying, okay, here's its initial speed. Okay, it had a speed prior to being let go, and then this is when the object is let go. Okay. Alright, so this is an interesting diagram. Your initial velocity here is never going to be 0. It's always going to, if you're going to throw something upward, you're always going to have some sort of initial velocity, okay? Then the ball, it doesn't have to necessarily be thrown in an arc. I'm showing it in an arc so that my arrows aren't right on top of each other. But let's just say I took a ball and I threw it upward. There comes a point where it stops moving in the upward direction and it starts moving downward. When it gets to that point where it stops moving upward and it starts moving downward, its velocity is 0. There comes a split second where it comes up, it rests for half a second, and then it falls down. It's not necessarily half a second. It's usually a lot less than that. But at the time, right here at the top of the curve, my velocity will always be 0. Okay? Here, the velocity is positive because I'm throwing it in the upward direction. Then the velocity is 0. Then the velocity starts to become negative. So your final velocity here will be negative. Even though we may not know what it is, we know it's negative. If you're looking, if I was to look on a dotted line right here, I could say that this velocity, my initial velocity, and my final velocity right here, if we're looking at the final velocity of the object right at the same distance, okay? So, for example, we're not looking at it right down here, okay? We're looking at the object right as it passes the same exact point at where it started. The velocities will be the same. Okay? So if I threw my velocity, for example, let's say I threw my velocity of this ball at 2 meters per second, a positive 2 meters per second. Then it would come up, it would reach a velocity of 0, it would come down, and right at the same position where I let it go, it would be a negative 2 meters per second, okay? And the reason why is because acceleration is always working downward due to gravity. Sorry, acceleration due to gravity. So I'm going to do a big A and a lowercase g. That represents acceleration due to gravity, okay? Big A, lowercase g, acceleration due to gravity. It always works downward. So as the ball's being thrown up, it's actually slowing down. Okay, it might start off with a high speed of 2 meters per second, but it's slowing down because velocity is positive, acceleration due to gravity is always negative. See how they're opposite signs? So your object slows down until it stops moving at 0 meters per second. The acceleration is still existing on it. So now the acceleration is, it's always negative, but now the velocity is negative. So since the acceleration is negative and the velocity is negative, the object speeds back up. Once it reaches the same point, the same position that it started at, the velocities are the exact same, it's just in the opposite direction. Okay? So, now that we have kind of a conceptual idea of acceleration due to gravity, we're going to do an actual problem. Okay? Here's an example problem. Whenever you're doing these types of problems, you have to do a diagram first. So, here the ball is dropped from rest. That means I know I'm doing a free fall diagram. Okay? It falls for 5 seconds, so this is change in time, before it hits the ground. What was its final velocity? Okay, so we know we're looking for VF, right? So, here's my diagram. A ball is dropped from rest. A free fall diagram, we always know our initial velocity. What is it? Well, if it says it's dropped from rest, it's 0 meters per second. So it drops. We know the change in time. It's 5 seconds. We want to know our final velocity right before it hits the ground. That's our terminal velocity. Okay, here's the ground. We want to know our final velocity right before it hits the ground. So then I want you to label your givens, which I actually did. So technically your diagram and your givens are the same thing. Okay, my diagram is the ball and the arrow, and then my givens are listed here on the right side. Then I need to label, what am I looking for? What am I trying to find? Well, it says I'm trying to find the final velocity. So we need to choose an equation that has all these variables in it. We need to find an equation that has our initial velocity, change in time, and our final velocity. Well, we know an equation that has all those things. I'm going to write it for you. It is our acceleration equation. Acceleration is final velocity minus initial velocity divided by final time minus initial time. So if I'm looking for final velocity, that's this right here, I need to rearrange the equation so that this is on the side of the equals all by itself. So I'm going to start by moving my TF minus TI to this other side. Okay. Now, how can I move it to the other side just like that? Well, I can multiply both sides by TF minus TI, okay? And so now I've gotten rid of it on the right-hand side. Okay, so now this is gone. Whoops. Accidentally took out my VI here. Okay, all I need left is the VI to be gone. So it's being subtracted, so I'm going to do the opposite. I'm going to add it. So it's gone. It means I'm adding it to this side. So my equation now, I'm just going to rewrite it so it makes a little more sense, is VF, final velocity, equals all of this right here. That's VI plus TF minus TI times acceleration. So let's just make sure I have all these. Do I have my initial velocity? Yes. Check. Do I have my TF minus TI? Well, I don't actually have final time and initial time, but I have what this represents. Remember, TF minus TI is the same thing as change in T. So we have change in T, so that means we have these values. And then do we have acceleration? Well, it's being dropped from the ground, and so I know the acceleration at play is gravity. Okay? So let's go ahead and plug in our numbers here. My initial velocity is 0. My change in time is 5. My acceleration due to gravity is negative 9.8 meters per second squared. So when I plug this into my calculator, I'm really just taking 5 times negative 9.8, and I get negative 49. Now that should make sense. Your final velocity in a free fall diagram will always be negative, because it's always going in a negative direction, which is makes sense because we're accelerating in the negative direction also. Okay, now let's do another problem. This problem, we're actually going to use a different formula. there's two formulas that have acceleration in them. The first one you already know. It's VF minus VI divided by TF minus TI. That is our traditional acceleration formula. However, we have another formula that we use when we're not given time. Sometimes I can give you something like distance, okay? And so we'll use this formula when we're looking for a value, but we're given distance. Okay. Let me just kind of walk you through this formula right here. Again, you never have to memorize formulas, don't forget. We just have to know how to use them. So this is final velocity, but it's being squared. This is initial velocity, it's being squared. This is 2, this is acceleration, and then this is your change in distance. Okay. So this formula you need to use if you're given time. This formula you need to use if you're given distance, okay? But you can use both of them with these free fall diagrams. Okay. The same information from above, now solve for how many meters the object fell. Okay, if we're using the same problem as above, here's my object. It's falling from rest, which was 0. We're not going to worry about the time right now. We're looking for final velocity. And we know the acceleration was negative 9.8 meters per second squared. But this time, instead of looking for, it says, sorry, I got this wrong. We're looking for how many meters? We're looking for distance. We actually know the final velocity because we calculated it, right? It was negative 49 meters per second. So I can use all of these to solve for distance. Let's first rearrange our equation. Well, the first thing I want to do is I want to move anything that's being added or subtracted to the other side. So I'm going to move VI squared to the other side by subtracting it, okay? Now I can get rid of that stuff. So let me see if I can erase it. Okay. Now what I want to do is I want to move my 2 and my AD to the other side. So if I divide by 2 times A, now I get D all by itself, right? That's what I want. So this is my formula then for distance. Okay, I just rearranged to solve for distance. So let's go ahead and plug that in. Distance is your negative of the final, the initial velocity, which was 0, plus my final velocity squared divided by 2 times my acceleration, which is still acceleration due to gravity. So this comes out to be just 0, and so negative 49 when it's squared is a really big number. It's negative 2,401, and then 2 times negative 9.8 is negative 19.6. So if I take those numbers and subtract them, let me do that real fast, I get 122.5, and that's meters. That's my distance that the object fell. Okay, I have one more problem I want to do with you guys. And this is going to kind of use the new equation that we just learned about. So Mrs. Millsap decides to go trampolining. She gets on the trampoline and jumps upward with a velocity of 1 meters per second. At what time does she reach the height of her jump, and how many meters upward did she jump? So we're looking for two things, okay? So let's go and draw our diagram. Well, I get on the trampoline, so here's me, wee-hee, and I jump upwards with a velocity. So I'm jumping upwards. So my initial velocity is 1.5 meters per second, okay? Jumping upwards, and just like any kind of jump, you're going to jump upward, and then you're going to come back down, right? That's how it'll work. So we know that my velocity right here, when I am at the highest point, what's my velocity? It's going to be 0, right? It says, what time did she reach the height of her jump? So we're looking for the time, not that it takes me to jump up and jump back down, but we're only looking for the time it takes me to jump up. So this is going to act as my final velocity in this case, because we're only looking at this time interval. And then I also want to know my distance for this jump. So I'm looking for these two things. So let's first just look for time. Okay, let's first find time. So how do we find time? Well, let's look at our two formulas. And then okay, so the first formula I want to use to get time is this one right here. This is the only formula that has time in it, so I don't want to use the second formula yet. So let's go ahead and rearrange to solve for time. Well, if I want to get time by itself, I can just multiply both sides by time and then divide both sides by acceleration. So really, time and acceleration just flip-flop their spots. So VF minus VI divided by acceleration will give me time. So my final velocity was 0. My initial velocity was 1.5. I'm going to divide by my acceleration due to gravity. So I have negative 1.5 divided by negative 9.8 meters per second squared. And so my time is 0.153 seconds. Okay, but since I only have two significant figures in this answer, I need to round it. So let's do 1.15 seconds. That's my time. All right, now I want to look for distance. Okay, what's my distance? Well, I'm going to use this formula to solve for distance. Okay, so I'm going to rearrange it the same way that I did earlier. So this is negative VI squared plus VF squared divided by 2 times A. So let's go ahead and plug in our numbers. Our initial velocity was 1.5. We square that. Plus our final velocity, which was 0, divided by 2 times our acceleration. So really I have 1.5 squared, and that's a negative, so it's really negative. And then I'm going to divide that by 2 times negative 9.8. And I get a distance of 0.11 meters, and I rounded to two significant figures, so that's what I have in my problem. And that's how you use both of these formulas to find time and distance. That is it for our free fall video. I hope that you had a good time and that you're thinking of the song Free Fallin', Free Fallin'.